So,
Ah, so it's a very simple
hello,
concept.
Kumar.
You don't have to. Ah, hi,
Okay.
Mukund is here. Anybody else coming or what's up?
We can start run.
Yeah, just a second. It's just loading. Have you started recording? Okay, so good afternoon, everybody here. So last lecture, I think formally we looked at Lagrangian mechanics, right? And how Lagrangian mechanics can essentially be looked at a way of simplifying the entire of Newtonian mechanics into one very elegant equation, right? So we are going to look at the motivation of expressing or finding out the Hamilton of a system, or in a sense, formulating Hamiltonian mechanics, right? So again, last lecture we saw about how the Lagrangian makes life much simpler for us physicists. For example, deriving Kepler's law. So I think we all suffered a lot in Sem 2 mechanics, right? Trying to solve Kepler's laws using that a lot of assumptions and a lot of derivatives. But then the Lagrangian provides us a way to simplify that a lot and then just elegantly solve the entire Kepler's laws of motion in just 2 or 3 steps, right? So now, what is the Hamiltonian? You might ask. It's for some people it might be new. For some people they might have already heard about it. But essentially, the Hamiltonian is derived directly from the Lagrangian. And when looked at the raw sense, or if you just look at the Hamiltonian, it's pretty simple. It's just H equals T plus V, right? Where T is the kinetic energy of a system and V is the potential energy of a system. So the kinetic energy and the potential energy summed together is the total energy of a system, right? So then this can also be seen in quantum mechanics, right? So we have all came across the H cap or the Hamiltonian operator, right? So what does that give us? The total energy of a quantum mechanical system. But for this lecture, we are going to mainly focus on the classical mechanics part, right? So Hamiltonian mechanics gives us the canonical equations of motion, right? So what do I mean by the word canonical? So canonical equations of motion gives us the normal equations of motion that we know in terms of the generalized momenta and the position of the particle, right? So if we look at the slide here, so the Hamilton's equations are written as qi dot equals dou h by dou pi dot, right? Pi, sorry, and negative pi dot equals dou h by dou qi dot, right? So nothing to fear here. So we are going to derive the entire set of equations in the next session. But a small gist that you have to know right now is that this is directly derived from the Euler-Lagrange equation, right? So if you recollect the Euler-Lagrange equation, it's essentially dou L by dou Qi minus dou by dou T in brackets dou L by dou Qi dot is equal to 0, right? So then if we take the potential energy of a system, right? So again, recollecting, brushing up your memory, the Lagrangian is nothing but T minus V, right? So then if we take the potential energy of a system, that is the V, to be velocity independent, then if you just do it yourself, or maybe this could be a proof exercise for you. So Pi will be equal to dou L by dou Xi dot, right? So then if we extend this, this definition, right, we can get the generalized momenta of the system, the Pj, to be equivalent to dou L by dou Qi dot, right? So now in the next slide, yes, so Pugal has written it down, thank you. So we'll be looking at how we are going to derive this entire set, and Pugal's going to do a brilliant job in telling you all how this comes up, right? So I'll be handing it over to you, Pugal. You guys can take a guess. It's not a
What?
one way.
What?
Yeah. Take in consideration the variables that we are using, right? So then, for example, the Lagrangian is qi dot and t. So what is the Hamilton? How is that written? So Yuvraj has given the answer as Hilbert space. So is that right? No? Yeah. So for the Hamiltonian dynamics, we use pi, qi, and t, right? So we have the generalized momentum and the position, right? So we use this elegant configuration space, also called as the phase space, right? So then, yeah, Pugul, you can go on. Yes, so we physicists just like to, play around with equations and see what we can get out of it, right? So if you go up a little bit, Pugul, just go to like the first thing, right? So we saw that the Hamilton is nothing but no mala. That is an up. Yes. So if we take that equation there, H equals T plus V equals to sigma PIQI minus the Lagrangian, right? So again, rewinding back to our previous lecture, we saw that for the principle of least action, right? So what does that state? So delta S is equal to 0, right? So if we rearrange this a little bit, right? So we get sigma PIQI minus H equals the Lagrangian, right? So then go down again, back to the initial slide, please. So yes, so what do we have here? Essentially the same thing above there, but then the action is essentially just the integral of the Lagrangian, right? If we recall the previous lecture. So essentially we just integrated that. So L equals the initial equation. I don't have the fancy pens and all to write down, so you gotta bear with me. So then, so delta of S, right? So essentially equals 0, right? So what we essentially did was we kind of repackaged the principle of least action in terms of the Lagrangian. So this is called the modified Hamilton's principle. It's just a very small interlude here, right? So then it's nothing significant, but just a small thing that we'd like to know. So go down. Yeah. Yes. So yes, now moving on to the Poisson brackets, right? So what are Poisson brackets? Poisson brackets is an important binary operation in Hamiltonian mechanics, right? So it's a very important mathematical tool that allows it to write derivatives, right, in a more elegant way, right? And then if we saw whatever we saw so far, Hamilton's dynamics are just derivatives expressed in a very uh, particular way, right? So we can see how Poisson brackets can help us express the Hamiltonian equations of motion in a more elegant way. Yes. So in this slide here, we can see how we can define Poisson brackets, right? So Poisson bracket of a comma b is nothing but the sigma over I dou a by dou qi dot qi dou b dou pi minus dou b, and you can go ahead, right? So then they have these properties, right? It's axioms that they follow, right? So they follow the antisymmetry, which is a comma c is equal to negative c comma a, and the bilinearity, right? So if you have a scalar, right? So a k in here, you can take it out of the Poisson brackets and express it as k Poisson bracket a comma c, and then they also have this commutative property, this so that you can essentially do it this way, right? So if you go down, right, this could be left as proof for you, but then we can rewrite the entire Hamilton's equation through Poisson brackets as pi dot equals pi comma h, right? So if you go up, we can see how it all works out. I think if you could write it out, it would be easier. Yeah, forward. If you go up, yeah, yeah, just go up. So go to the Poisson brackets part, right? Yes. So here we can see if we substitute pi and h, right? So then what happens? The pi and pi cancels, right? And then you get dou. Yes. So then you get dou h by dou qi minus, and then here what happens is the qi cancels out, right? So then you can see how the entire equations of motion in terms of the Hamiltonian can be written in terms of elegant Poisson brackets, right? So then go down. Maybe we could share this slide with them so they could like work it out themselves in their free time. Yes. So then here we can see that qi comma tj, right, is equal to the Kronecker delta, right? And essentially what that says is it just cancels out, right? So you get 1 minus 1 on the thing, and then you get the Kronecker delta, right? So Kronecker delta is the identity. Am I right, Pugal, by saying that? Yes. Yes. So we could go down. Okay, so these are just another examples of how you could repackage the equations of motions in terms of Poisson brackets, right? So yes, Pugal, you can take over from here. So now we are going to look at a much more simpler theorem than the Liouville's theorem was quite a handful. So we're going to look at a much more simpler theorem called the Virial theorem, again derived from the Hamilton's principles, right? So what is a virial, you might ask, right? So let us consider a system of particles with generalized momentum pi and right. But then here's the catch: they are it's a bounded system, right? So that provides that it's conserved. Momentum and the particles inside are conserved. They don't suddenly vanish somewhere, right? So then let us define a quantity S, right? S is just an arbitrary quantity, which is the sum over I of Pi dot Ri, right? So then now let us take the time differential, right, of S. So we can see this is very simple. This is just a product rule applied to equation 4. So we get Pi dot Ri plus Pi dot Ri dot, right? So then now we are going to do a small mathematical trick. We are going to try to find out the average, right? The average time derivative of S, right? In the time interval of tau, right? So then how do we do that? We just integrate it with respect to dt with the limits of tau, right? So I don't think that's an r there. I think that's a tau, okay? So then 1 by tau integral of upper limit tau and 0 ts by dt, right? So then this just simplifies to s of tau minus s of 0 minus tau, right? So then this is integral, you're just taking the s out. This just simplifies to just s and then you're just substituting in the limits, right? So what happens here is we considered the system or s to be a bounded function, right? That was my first assumption. So when this function is bounded or if it is periodic, right? So then essentially what happens to this value right here, right? It tends to 0. Why does it tend to 0? Because if s of tau and minus s of 0 is bounded, right, it can't extend to more than, let's say, a finite value. But then what we can do, the time interval we can increase as much as we want, right? So then by making the time interval large enough, we can essentially make this entire term negligible, right? So then go down over. Yes. So essentially what we did there is the equation above, we just equated ds by dt to 0 and then we took the summation to the other side. So this is the result we get, right? So then a small note to be made here is, if you see the left hand term right here, right, that is nothing but mv squared, right? So then what is mv squared? We can take it as twice the kinetic energy, right? Because 1 by 2 mv squared, and then you just multiply that into your kinetic energy, and the right hand side, the pi dot is essentially just the force on that system, right? So then we just substitute fi into that. We take the 2 to the other side, and we get the average energy of a system. Average kinetic energy of a system is equal to negative 1 by 2 summation over I FIRA, right? Now, the right hand side, right? This is called the virial of a system, right? So what does equation 19 tell us? It essentially tells us that the average kinetic energy of a system is just equal to the virial of a system, right? So then why do we do this in the first place, right? So that is why we're going to take a look at a toy model or a small application of this virial theorem in the dark matter hypothesis, right? So Fritz, you can look him up. He was the first guy who suggested that there is something called dark matter, right? So how did he do that? That is the question, right? So if we take the virial of a system, right? So Fi dot Ri, which is the virial, is nothing but f sigma of sigma fji dot rji, right? And here, what a small assumption that we're making is we are using Newton's third law here, that Fij equals to negative f ij, right? So then I think it's ji. Wait, let me just check. One sec. Yes, it's ji, right? Which is just Newton's third law, right? So then we are just using that. We're just substituting that into this system right here, and then you can essentially just skip this. This is just trying to find out the rji of the system, right? So then go down a bit, Pugar. So this is very simple, okay? You don't have to like bother about this. All of this is just little manipulations. Go down. Hello. Yep. So yes, we come up to this equation right here, right? The virial of a system equals to negative g m1 m2 by rij cube rji into rji, right? Then again, let's just ignore this and then let's just consider fji to be what? gm1 m2 by r square. That is pretty simple. We all know that, right? So then there is a dot rji outside, right? So then what essentially happens is the rji at the bottom essentially just cancels out with the rji outside to give you the final equation, right? The equation 22 to be gm1 mimj by rij, right? So then Virial theorem states that what? The virial of a system is equal to the average kinetic energy, right? So then what is the average kinetic energy here? Which is 2 mi vi dot, right? But then here there is also 1 by 2 here according to our equation, the first equation. So then that cancels out and then we get this term on the left here, which is technically called the wait a second. Yeah, it's called the mass average squared velocity, right? So then this is the theory here, right? So then what did Zwicky do is the more interesting question, right? So then he essentially calculated the mass of the coma cluster, right? Which is essentially a cluster of galaxies, right? Which is a bit, I don't know the distance, but yeah. So he essentially calculated the mass of the coma cluster, right? Using this equation right here, because these values are pretty known. The gmj by rij essentially just becomes one huge constant, which if you studied quantum mechanics or general relativity using the appropriate units, you can usually make it into unity, right? So then he measured the mass of the galaxies, of the galaxy cluster, right? And then he tried to find out whether it was equal to the mass found out by the galaxy's luminosity. Okay, then what he found out was that the luminosity and the mass found out by the luminosities and the mass found out using the Virial theorem was completely not agreeing with each other, right? The mass found out by the Virial theorem was completely outshadowed by the solar lumin. Sorry, it's the other way around. Yes, the solar luminosity mass was much lesser than the Virial theorem mass. Okay, so that led to Zwicky hypothesizing that okay, there might be something called as dark matter, right, contributing to the overall mass that we cannot directly calculate from the galactic luminosity, right? So this is a very interesting application in astrophysics. As you know, astrophysics is like the catchphrase, no? Astrophysics, no, it's very interesting, right? So then we thought we'll just add this in. So I guess that ends the lecture, right? I will also be linking you the article that I used for this Fritz Zwicky hypothesis. So it has much more detail on all the exact values because it's quite a mouthful to say it out. So yeah, I think we can conclude here.